Welcome to the Explainer. Today, we're going to do something a little different. We're not just going to talk about a certification. Nope, we're going to get inside the head of a modern AI architect. And we're going to do it by digging into some really cool insights from the Google Cloud ML Engineer Practice Exam.
So this quote right here, it's perfect. The ML engineer designs and creates scalable performance solutions. This really gets to the heart of it. We're not talking about someone who just sits in a lab theorizing. No, this is about being a builder, a strategic builder who owns the entire AI solution from the first line of code to the final product. It's all about making stuff that actually works, at a massive scale and when the pressure is on.
All right, so here's how we're going to break this down. We're basically going to follow the life of a real-world machine learning project. We'll start with the architecture and the data, then we'll tackle the tricky parts of training and evaluation, and finally, we'll get it out the door into production.
So let's kick things off. What does it really mean to be a professional ML engineer, especially on a platform like Google Cloud?
I like to think of this role as being a kind of tech triathlon athlete. Seriously. First, you've got the data engineering leg. You're wrangling massive, messy data sets. Then you switch gears into the data science part, building and evaluating models. And for that final sprint to the finish line, you have to be a top-notch software engineer to get it all into production. You got to be great at all three. It's a huge job.
All right, so where do we even begin this whole process? Well, it's the same answer every single time. It starts with the data. You've probably heard it a million times, great models are built on great data. And it's absolutely true. But you know what's also true? Spectacular failures, they often start in the exact same place. Okay, let's imagine this scenario. It's a classic one. Your model is looking amazing. You've got this great validation score, an AUC of 0.80, which is solid, right? You're feeling good, so you push it to production. And then, all the alarms start going off. The model is just not performing in the real world. So what happened? Well, 9 times out of 10, the culprit is a really fundamental problem with your data.
And this right here is a textbook example of something called training serving skew. The problem? That simple, flawed RAND function used for splitting the data. It's like you gave a student the answer key to study for the final exam. Of course they're going to ace the practice test, but have they actually learned anything for the real exam when the answer key is gone? Nope, not a thing.
So how do we stop this from happening? Well, the first line of defense for any good ML engineer is a tool like TensorFlow Data Validation, or TFDV for short. Think of it like a bouncer at the door of your data pipeline. It's got a strict guest list, the schema, and it checks every single batch of data coming in. If something looks off, if it's not on the list, it gets rejected. That way, bad data never even gets a chance to poison your model. Okay, so let's say you've got your data pipeline locked down. Everything is clean, your job's done, right? Not even close, because now you have to actually train the model. And the training process, well, it can be a real puzzle. And sometimes those pieces just refuse to fit together. So picture this. You're watching your model train, you're looking at the graph, and the loss line, it's just this flat, horizontal line of pure disappointment. It's not learning at all. Now, your first instinct might be to start messing with all the complex hyperparameters. But the real answer? It's to think way, way simpler first. And this is such a great, repeatable debugging process. The most important step, the very first thing you should do, is test it on a tiny little data set. I'm talking like 100 examples. Can your model even learn from that? Can it overfit and drive the loss down to basically zero? If it can't, you've got a much bigger problem somewhere in your code or your data pipeline. It's such a simple sanity check, but it can save you hours of wasted time and money.
Okay, but what if the opposite is true? The model is learning, it's just taking forever. This is another super common problem. Let's say your scikit-learn model is just crawling along. You've got to find a way to speed it up, and that's where something like Vertex AI comes in.
And here's the real pro tip. Always, always look for the cheapest and fastest win first, before you go and do a massive rewrite of your code or set up some super complex distributed training system. Just try moving your existing code to a managed, optimized environment, something like Vertex AI training. That simple step alone can give you a huge speed up without all the extra work.
All right, so we've got clean data, our model is training, and it's training fast. We're golden, right? Well, how do you know if the model is actually any good? This is where we hit the evaluation phase.
And this is where a high accuracy score can be one of the most dangerous lies in all of machine learning. Just take a look at this. Let's say you're building a model to detect a logo in an image, but only 4% of your images actually have a logo. A lazy model could just predict no logo every single time. And guess what? It would be 96% accurate, but is it useful? Absolutely not. It's completely useless. This is what we call the accuracy paradox. It looks fantastic on a report, but the model hasn't learned a single useful thing. And this is exactly why smart engineers use something called the F1 score. I love this analogy. Think of it like a search and rescue mission in the woods. You need to find all the actual lost hikers, that's your recall, but you also need to make sure you're not scrambling the helicopters for every squirrel that moves. That's your precision. A high F1 score means you're doing a great job at both, finding the hikers without chasing all the squirrels. And this becomes so important in high-stakes situations, like predicting when a critical machine is about to fail. Missing a real failure could be incredibly expensive, or even dangerous. So in that case, you're going to prioritize recall. You want to catch every single potential failure, even if it means you get a few false alarms. The goal is to crank up that recall as high as you can, while just making sure precision stays at a reasonable level so you're not sending the maintenance crew on a wild goose chase every 5 minutes. Okay, we're in the home stretch, the final phase, MLOps. This is all about taking your trained, evaluated model and making sure it actually works reliably in the real world. And, just as important, that it stays relevant. Honestly, this is where the engineering part of ML engineer really shines. Because once that model goes live, the engineer's job basically turns into being its guardian. You are constantly on the lookout for that training serving skew we talked about. You're watching for any signs that the real world has changed, we call that concept drift, and that your model's old assumptions are just wrong now. And all the while, you have to make sure the whole system can actually handle the traffic without falling over. And this really gets to a core trade-off that engineers have to make constantly. The best strategy for monitoring isn't just about being the fastest to catch problems. It's about finding that perfect balance between cost and speed. For example, maybe you sample just 10% of your traffic every hour. That's often good enough to detect problems pretty quickly, but it doesn't break the bank on your cloud bill. You only trigger that super expensive retraining process when you absolutely have to. So when you think about it, from fixing a single bad line in a SQL query that's causing data leakage, all the way to debugging a model that just won't learn, and then designing a whole cost-effective monitoring system, that is the world of the ML engineer. They don't just own the model, they own the entire system from end to end.
And I think that's the key takeaway here. The best solution isn't always the fanciest algorithm or the most complex architecture. It's about judgment. It's about knowing which principle, which tool, which metric to apply at the right time. The challenge isn't just about the code. It's about making smart decisions. So the real question is, are you ready to build? Thanks for joining this explainer.